Okay, so our next speaker is Dr. Calliope-Louisa Sotiropoulou. I hope I'm pronouncing that correctly. Who is an electronic engineer, and as you may remember from yesterday, she holds the position of sales engineer at CAST and specializes in the image video data compression IP stacks. And previously to that, she also had a long career in research and development, and she was also working here at CERN in the Atlas experiment. So please welcome Calliope, who is going to talk to us about accelerating data for data centers.
Great idea to use lossless data compression. Because it enables you to compress your data without losing any kind of information. It is numerically accurate when you decompress. When you decompress your file, you get the exact data at your input. This means that there is no impact on your AI, no impact on your scientific calculations or scientific precision. And it reduces radically your storage and bandwidth requirements. Even a modest compression like a 2-to-1, okay, 2-to-1 is actually a very good compression for lossless data compression, will give you a 50% cost reduction. And consider that 1 petabyte of storage of a data center annually costs around $100,000. Okay, that's a lot of reduction, 50% at this kind of numbers. And it also multiplies your effective bandwidth. So if you have a 2-to-1 compression, effectively, your 100 gigabps link on your FPGA device becomes 200 gigabit per second if you use compressed data. Okay. So what is lossless data compression? It's a method of reducing the size and the data of your stream so that the original data can be fully and perfectly reconstructed. Lossless data compression algorithms usually consist of two steps. The first step is a search algorithm that is a kind of window that you move over your data and you identify redundancies, patterns that are repetitive. And then you encode it in a way by using some kind of encoder that could be Huffman, it could be FSC, it could be dictionary encoding. And this two-step process is your lossless data compression algorithm. Now we will focus on a group of lossless data compression algorithms that are based on a search algorithm that's called LZ77. Okay. This consists of GZIP, LZ4, Zstandard, and Snappy. I guess most of you have heard or have used something because they're all available on your Linux root. Okay? So when we use these algorithms on software, there are certain implications. GZIP, that has two flavors with dynamic Huffman tables and static Huffman tables, can have a high or a moderate compression ratio, a high or moderate latency, and a moderate speed. LZ4 and Snappy have a lower compression ratio, low latency, and high speed on software, while Zstandard has a high compression ratio, high latency, and moderate speed. Okay. This is what happens in software. So software is good, but hardware is better. Why? Software is flexible, but it creates a very high CPU load. Okay. It scales poorly, especially on the throughputs that are required today, like hundreds of gigabits per second. You cannot scale that on CPUs and GPUs. And most importantly, it has an unpredictable latency. So this means that we have unpredictability. It cannot be used in real-time applications. Okay. Think what I used to do here, for example. How can you expect software to have the precise latency so that you can get your data at the very nanosecond you expect it? It cannot be done. Hardware instead offers deterministic performance, deterministic latency, deterministic throughput, and power. It can scale to multi-gigabit per second throughput. It consumes less power, so you have the equivalent of software and hardware, obviously. For the same throughput, hardware will consume much less power than multiple GPUs and CPUs you will need to process the same throughput. And of course, it's real-time ready, exactly because it is predictable. So what happens when we implement these algorithms on hardware? The same exact algorithms. GZIP with dynamic Huffman tables has high compression ratio, high latency, and high resources. With static, low latency and low resources. LZ4 and Snappy, again, they have low latency and low resources, while Zstandard keeps its characteristics of high latency and high resources. So different algorithms have different characteristics of latency and compression ratio. Okay, so is this information enough to choose which algorithm you want for your system? No, unfortunately, it is not. And why is that? Because lossless data compression is always data dependent. Not all lossless data compression algorithms work on the same way on all kinds of data. So what do we do to evaluate which algorithm is the best? Unfortunately, we cannot use, obviously, all kinds of data with all kinds of lossless data compression algorithms, but there are some benchmarks, some points of reference. One of them, which is most commonly used for this kind of applications, is the Silesia corpus, which I guess this is the pointer, which you can find on this link here. And we use this by using these algorithms with the same size of search window, 32 kilobytes, so that we have a point of reference to compare objectively all algorithms. And you use the aggregate compression ratio. It's not the average. The aggregate also takes into account the size of its file. The definition is right here in the slide. And by doing that, we can see that GZIP with dynamic Huffman tables has a higher compression ratio for the Silesia corpus, while Zstandard and GZIP with static Huffman tables have a similar compression ratio, like 2.7. LZ4 and Snappy have a lower compression ratio. Okay, this is more or less what we expected. So what happens when we take into account that we want to implement this on hardware? Okay. And we want to have high throughput implementations. So this means that we have to implement multiple parallel processing cores. The cost becomes higher with resources. And especially on FPGAs, as I said before, that your resources are limited, it is also important to take into account that you also have limited memory resources, BRAMs and URAMs. And what you have at high cost is the history window, which always needs to be stored on BRAMs and URAMs. Okay. So the larger the history window, you have higher compression ratio. So the higher the window, though, you have more memory that you need to use. So you need to sacrifice compression ratio in order to save resources. So what happens when we limit the history window? So here's what we did. We did the exact same study by changing the history window from 1 kilobyte to 32 kilobytes. And you can see the impact on all these algorithms. You can see the impact is, of course, smaller in the lower compression ratio algorithms such as LZ4 and Snappy. And you can see that the GZIP starts by 2.4 and ends at 3.1. Okay, so this is the range for 1 kilobyte. Of course, the history window can even become smaller, depending on the application. This is just an example to give you a range. This is one thing to take into account. Another thing to take into account is that there are a lot of applications, especially in data centers, that limit the size of your files and your data into blocks. Data centers use paging, and the most common size is 4 kilobytes. Can be 16 or 64, depending on the application. The most common is 4 kilobytes. And the smaller the file, the more difficult it is to compress it. So what's the impact of changing the history window size when you have smaller files? This is important to understand because data centers are the #1 application right now that use lossless data compression. We can see here the change between 1 to 4 kilobytes of history window size. And as you can see, the impact is smaller of reducing the history window size when the file is smaller. And again, for LZ4 and Snappy, it's practically non-existent. But I guarantee you, from experience with our customers, customers are willing to sacrifice a lot of resources to gain even 0.1 and 0.2 of compression ratio in data centers today because it saves a lot of money and a lot of processing speed. So this is just to put it into perspective from real-life applications. So to summarize, the history window can be less than half of the size of the file without compromising the compression ratio. So let's discuss FPGA compression. It can be integrated in a very easy way on a modern data paths. We have cores that can be streaming, and they can be used inline easily between your Ethernet memory, with your memory storage, your Ethernet, and your Mac. Okay. We have PCIe's and NVMe's accelerators. And we have speeds of like PCIe generation 4 is at 32 gigabytes per second. The latest generation of PCIe reaches 128 gigabytes per second. Your traditional SATA SSDs max out at 550 megabytes per second on access to read and write. And your modern NVMe SSDs max out at 14 gigabytes per second right now. So you can see the speed of the input of the interface, it's much higher than what you can do to write data. So you need to use some compression there in order to be able to cope with the speed. You also save on bandwidth for your DDR and your high of HBMs and HBM interfaces. You have fewer accesses to the memory, which means significant power reduction. And you also reduce data traffic on sensor and acquisition pipelines. And what is very easy for embedded systems developers is that most of the cases, the software layer doesn't need to know that there's compression there. These cores that I'm explaining, I'm describing right now, don't need drives, don't need any processor, they don't need any software, just need to program a few registers, they just do it. So your software layer, pre-existing software layer, doesn't need to know they are there. They just work in the background. So there are some key trade-offs to discuss. Latency versus compression ratio. The higher the compression ratio, the higher the latency. It will be thousands of clock cycles. Lower compression ratio will lead to algorithms that will have tens of clock cycles of latency. Throughput versus FPGA usage. The higher the throughput, the more the resources. The throughput grows linearly. And then you have power efficiency. So how can we increase the throughput? We can increase it by incrementing, by multiplying the processing elements, making more processing elements work in parallel, or increase the clock speed. But of course, you hit the limit on an FPGA. And we need to choose the right algorithm for the workload. As we said, it's always data dependent. So talking from my experience and the CAST portfolio, and in my experience for most of these cores, we are the only ones that can offer them. We offer low latency cores that implement LZ4 and Snappy and GZIP with static Huffman tables with very few clock cycles of latency, and high compression cores with GZIP, dynamic Huffman tables, and Zstandard, and combinations of the above. All these cores can go to over 100 gigabits per second on FPGA devices, and even higher on the newer generation ones, like the big Versals, the Agilex 7s, etc. And of course, on ASICs, we hit much higher than 400 gigabits per second. We have customers that go to 800. Here are some real examples of customer implementations, just to help you understand the orders of magnitude. This is 100 gigabps system on an Alveo board with a dynamic Huffman table. It has around 660 kilolutes and 12,000 cycles of latency. If you switch to a static Huffman, it becomes 1/3 of the size, even less, and has a latency of 150. The equivalent happens to the decompression. And the decompression always is, as a core, is much smaller than the compression core. This is by definition of the algorithm by design. Switching to the LZ4 Snappy cores, we can see here again that we have low latency, but for 64 gigabits per second, even on the Agilex 5, we have 100K ALMs. And the UltraScale Plus, we have like 63,000 LUTs. On the decompression, for whatever reason, the synthesis of the Arctic 7 doesn't want to use memory. It just implements it all flops. But the sizes are more or less equivalent. We can see the same trend that the decompression, the equivalent decompression is much smaller than the compression. So these results are only indicative, and the cores are completely technology agnostic in the sense that they are developed in Verilog, and they can be implemented, and they have been productized on all FPGA vendors and ASICs as well. All results are scalable, and each configuration is design and application specific. So some takeaways to conclude this presentation. Lossless data compression is becoming a fundamental part of how new embedded systems are developed because of the latest application trends and the data explosion. There isn't a unique solution for all systems. Every system is different, so we need to find a specific solution based on the requirements. We need to know the technology, the throughput, the compression ratio, the latency, the clock frequency the customer wants, what kind of data they will use, and we will propose the right system. High compression ratio solutions come at the expense of using more resources and higher latency. And it is fundamental to have an easy integration on your system. So you need to have easy-to-use interfaces and easy-to-use memory accesses. So it is very important that the developer makes an educated decision. So this is why it's good to rely on experts that have done this many times before, for more than a decade, such as us in CAST. So to summarize, lossless data compression is beneficial, but implementing it is complex. So I'm here to take your questions. And if you want more information on the course, you can go to the website to find specifically more information, or ask me right outside. And now, of course. Thank you.
Thank you very much. All right, then, who has questions? Yes, go ahead.
I have a question. So, to my understanding, or of course, I have also the problem that I have a certain memory size only, but want to put more data in, so I should compress it.
Yes.
But the problem is, of course, that if I have, for example, my stream is coming and put it into blocks, and then make a compression of this block, it's not predictable what the compression factor will be, because it depends on the contents of this block.
Yes.
And my problem is, at the end, I want exactly to get data at a certain point in time, and if it now puts all these blocks in memory, then because of the different block sizes, I cannot predict which block I have to get out. You understand what I mean? If I have a data stream with some traces and I compress it, and I would then at the end get out at a certain point in time, so a certain part of this trace, but the compression is different, effective, and I put this in the memories, and at the end, I don't know where to look in the memory for a certain point in time to find the right.
So let me see if I understand correctly what you have data that arrive. Are the data on a fixed block size or different blocks?
No, they are coming every nanosecond.
Every nanosecond you have a sample.
Yes,
of
for example, yeah.
Every nanosecond you have a sample.
Yeah.
Is the sample size fixed, or it can be anything?
No, the sample is always 28-bit.
The sample is always 28-bit. So you don't know how to you compress it, but you don't know if the output would be the size of the output, because it's unpredictable. Yeah. Okay, that's the nature of lossless data compression by definition.
That's the problem.
So, and you need to have the reply out at the same rate as the compressed the uncompressed input.
Yeah, yeah.
And your problem is that you need to put it in memory sectors.
Yeah, something. Maybe we can discuss.
Yes, we have done similar things. This sounds to me like a problem, similar to a cache access problem, because you need to you have some kind of alignment in order to find the data, because you have different sizes of the output, compressed output, and you need somehow to align it in order to be able to relocate it and process it. But yes, there are solutions, because this is the unpredictable nature of lossless data compression, because you don't know for each data, what kind of compression ratio you will get. You can get 1.1, 2.3, it depends. So yes, that's an expected problem.
Okay, thank you. Other questions? At the back over there.
Hi, I have a question. So let's say you have two FPGAs, you have one optical link, and you have a lossless compression scheme. So my question is, can you tolerate bit errors, or you have to reinitialize the links and the FIFOs related with the compression?
So that depends on the algorithm. Okay, so there are, of course, error flags obviously. The GZIP, it depends on the compression algorithm you choose and on the package you use for transmission. The GZIP algorithm, for instance, on the decompression side, needs to decompress the complete file. So if you have a serious error in the file, you lose the complete file. And this is not something from the core. It's an algorithmic protocol. GZIP works like that. LZ4 and Snappy instead, and Zstandard are block-based. So you will lose just a block of data, and that will depend on the block size you defined when you configured the algorithm. So there are, of course, this is standard process when sending data over links, and there are ways to recover. You will, and what you want to do is to predict how much data you will lose, and you make it the smaller amount possible.
But when that happens, will you lose your synchronization?
Sorry?
When that happens, can you lose your synchronization, like a frame goes out of alignment with the other links that use lossless compression?
That depends. That doesn't have to do with the lossless data compression core. That depends on how you handle your links.
Yeah, I was thinking because you have FIFOs. If you have a missing word, maybe it's differently interpreted and written into a FIFO. Anyway. Okay.
Yeah, no, I can reply because this is more a system development and system design issue than a core issue. The core can recover. You will, and it can be configured to lose the minimum amount of data. How you recover your links is more of a system issue than a lossless data compression issue, because you have other things there. You have the link, you have the file, you have whatever processes your link, you have the FIFOs. It depends on how you design, and there is always some give and take, right? Depending how big your FIFOs are, small your FIFOs are, how much time you need to resynchronize your links, etc. But this is system design, not core specific for the lossless data compression. This is what I'm trying to explain.
Okay, thank you. Any other questions? No? Okay, then thanks, Calliope, again.